So, if everyone's here, this is about real-time is coming to Linux. Now, you might be all laughing about that because we've been saying that since 2004. Maybe not 2004. I think we were saying it around 2008. So the whole joke was, this is a year, real-time is going to be merged into Linux. It was like saying this is the year that, Linux is going to rule the desktop. It was equivalent. This time we actually mean it. And how do I know we mean it? And how I know we mean it this time is the fact that all our focuses, our talks, our meetings are not about what do we need to do to get real-time into Linux. All the meetings are now like, oh crap, we're getting into Linux. The job's not done. Not the fact that it's not done, that there's not more work to do to get into Linux. It's saying that our job's not done is once it gets into Linux, there's a whole new set of problems that come up. One thing is, it now needs to be maintained. Kernel developers can't break it. If it does, it's our responsibility to teach them not to break it again. So before I go further ado, I have to get my, selfie. Oh, shoot, the battery died. No! Oh, crap. I can use my phone, but that's cheating. So no selfie today. The battery just died. That was a first. OK. So who is this talk for? Well, it's mainly for Linux kernel developers. How many Linux kernel developers are here? OK. How many people are not Linux kernel developers? About 50-50. I'm actually pretty impressed. Pretty good. So if you do core kernel, driver code, file systems, pretty much anything that touches the Linux kernel, this talk is for you. And it's also for those that are just curious about what is this weird thing we call preempt RT. What makes it different? It's also for those who want to see how fast I can talk. So, what is real time? It's kind of like the question of saying, what is your favorite color? So the term is ambiguous. I always hate that term. So I looked it up this morning. Actually, I started writing these slides at 5 a.m. Seriously. And I went there. I'm like, what am I going to talk about real time? Let's see what the internet says about it. So I went to one of the most common sources of information, Urban Dictionary. And I got there. It says real time, instantaneous, taking place at once as all other things are also in progress. When I survived the situation in real time, there were only 4 people who met the qualifications. Or surveyed, sorry, survived. Surveyed. Instantaneous, simultaneous, blah, blah, blah. OK, I was actually pretty impressed that from Urban Dictionary, it had something decent. Then I went to whatis.com, and it says, real time is a level of computer responsiveness that a user senses as sufficiently immediate or that enables the computer to keep up with some external process. I need definitions for that. It continues. Real time is an adjective pertaining to computers or processes that operate in real time. I love definitions that include what you're trying to look up is included in your definition. And it actually had more. Real time describes a human rather than a machine sense of time. Actually, I think that's the most accurate. So that's not what I care about. I hate the term real time because it has all these means. You have real time tracking when you get UPS or you go to Amazon and you get your package and you hear all this real time. But the question is, what does it mean to us, the preempt RT, AKA the real time patch? By the way, that's another hint why it's getting into Linux. We no longer call it the real time patch because it's not going to be a patch anymore. And we call it preempt RT now. It means determinism. Has nothing to do with speed. It has to do with knowing what's going to happen. So we care about latency. We always calculate what's the worst that could happen. I like to say it's knowing what will happen when it will happen. So that's what really real time is to us. I always say it should be not called a real time operating system. It should not be an RTOS. It should be a deterministic operating system. So what's our strategy to making Linux into a real-time operating system? Well, the first thing is we have to make it as preemptive as possible. We want anytime a high priority task wants to do something, we let it do it as quick as possible. So let the user determine what's important, and as soon as their defined task of importance wants to do something, it should be able to do it. And give it as much power as possible, and try not to interrupt it in any way. So we try to remove preemption and interrupts everywhere that we can. So we can always have scheduling as powerful or everywhere. So always let the most important, highest priority tasks run when they want to run. That's what we try to do. So when real time comes into the Linux kernel, and you go do make menu config, and go to processor types and features, there's going to be a window that pops up in the preemption. There'll be a preemption model. Before the first three is only what's there today. You'll see the first three: no force preemption, voluntary kernel preemption, and preemptible kernel, Linux desktop. Two new things are added. And for full preempt RT, that's what we get. So no force preemption is the old days. I only know, does anyone ever run with no force preemption with our config preempt none? Anyone do that? A couple people? I almost want to say why. Voluntary preemption is probably, that's mostly the default. Red Hat, I believe SLS, Debian, voluntary preemption. Basically, anytime you hit like a might sleep within the kernel, it will say, hey, there was a debugging option called might sleep to trigger if you had a case where you're in a critical section and you called this function, and it might have a path that it might sleep, because a lot of times what would happen is you could run your code and everything's fine, but there might be a function with a path in it that will actually go to sleep, and you'll sleep while holding a spin lock, and your system will crash, and we're like, oh no. And these bugs kept boiling up. So throughout the kernel, we put these might sleeps throughout the kernel, so that if you hit a function that might have some strange conditional path to a sleep, you'll know right away that, oh, we can't call this function from a critical section, let's call something else, or let's fix up our code. So that solved a lot. Well, what they realized was all these might sleeps that are scattered out, because these functions can sleep, we can sleep there. It just also told us that this function, even though there's one little path that might sleep, it means that we can sleep. So voluntary preemption took up on that and said, hey, when we hit this might sleep, if there's a scheduling, something needs to be scheduled, let's schedule right there. So that's what voluntary preemption is. It took this debugging app option that helped save us from calling these might slips, and just used it to say we can schedule because we know this function can sleep. It's okay to sleep. It's okay to schedule out. Let's use it. Great. It actually helped a lot. I would love to get rid of server none because it's pointless. I think the might sleep ones are perfect. Then preemptible kernel is what we have today, low latency desktop. That's where basically spin locks become preemption points. So when you grab a spin lock, it will disable preemption, and you could sleep almost any time you're not holding a spin lock or don't specifically say, I don't want to sleep. So that's throughout the kernel. So it's actually very, very, very reactive. It's basically a soft real-time system. But we have two new things. The one I'm going to kind of ignore is just the first one, basic RT. That's more for testing purposes on us. But the next one is where it's full preempt RT. And this is why we call it preempt RT, because that's the config option. So if you're wondering why we always say, hey, it's the preempt RT patch or preempt RT now and not the RT patch, this is why, because it's going to be a config within the mainline Linux kernel. So interrupts as threads. You can always do, one of the things to help get a preemptive kernel is to have interrupts be able to thread. Because if you have a long-running interrupt, you can't do anything while it's going on. So we have to be able to preempt it. So the only way you can make it preemptible is it has to have its own scheduling context and be able to switch. So request IRQ or request threaded IRQ, it's been there since 2009. How many people have used request threaded IRQ? Hey, good, thank you. Appreciate it. Awesome. Because that's even in mainline kernel, your thread is or your interrupt is not keeping important processes from running. That's nice of you. Also, if you ever want to do it, there's this thing called threaded IRQs, which was added as a debug option to debug certain criteria, when it was really because we wanted to get our RT Linux, our real-time patch into the kernel. So a lot of times we would dress it up as a Trojan horse and say, hey guys, this helps you so much. This is something, we always had rationale that had all the real-time patches that made, or all the real-time stuff, or all the patches that came from the real-time patch were basically hidden as gifts to developers. LockDep came from the real-time patch. Mutex came from the real-time patch. Let's see, generic IRQs, making all the IRQ systems basically into core architecture, it came from the RT patch. This was because we couldn't do RT without it. But people like the code, like, hey, this makes things cleaner. Because one thing is, real-time patch requires clean code. So our gifts are cleaning up code to give to you. So, but this one was kind of like, hey, you could debug your system with making all your threads or all your interrupts threads. That way, if you have something crashing, you could debug it easier. That was our rationale. That's what we said, our rationale. But almost all the threads, everything becomes threads except for maybe, if you explicitly mark it to say no thread, and those are timer interrupts, IPI processors. Don't get saying, my interrupt is so important, I don't want it ever to be a thread, because people will hate you for that. Just to let you know. Normal interrupt handler is basically, so you have a high priority task, and this is why we don't like interrupt handlers that are not threads, because they'll preempt the task, the handler has to finish, and boom. So when you request an IRQ, you're given a single function called handler, which is a function that's going to run when your interrupt vector is triggered. When you do a request threaded IRQ, you're given a handler and a thread function. Now, the way that happens is when your handler executes, it'll go up, do the handler, and this way, if you want to shut off your device, because say if you have a shared interrupt line, then you have like a big long, if you have one of your threads or your handler takes a long time shared with other devices, you may want to run it as a thread. This way you could go acknowledge your device and then go away and just do your handler. Amazing enough, I searched the kernel and very, very few people do this, which is actually a good thing, and I'll explain why in a second. When you do forced threaded interrupts, which is basically when you enable preempt RT, it does the forced threaded interrupts becomes on. And what that does now is you have the interrupt triggers. You can't stop interrupts. The hardware that's a mechanism of hardware. So you trigger the interrupt, and you say, OK, all it does, the interrupt says, OK, we're going to disable that interrupt line, and then wake up the thread for the interrupt thread to handle everything else. So basically, all we do is turn off the line, so no more interrupts will come in, and we wake up a thread, and that's all that. So I would have made that smaller, the interrupt smaller, but then the word interrupt couldn't fit in there because it's really actually this is not to size. It should be a sliver. So interrupt goes off, boom, right back. So it's really, really fast. A microsecond at most. Then it runs your high priority task, and when your priority task you schedule. Now here's a kind of an interesting thing. If you use both, I say if you have a top half and a bottom half, now I'm sorry, but you're going to have two scheduling switches because your top half is still going to run as a thread, and your bottom half is still going to run as a thread. So we're working on ways to make it run as maybe a single thread, maybe so that get rid of the schedule switch. We're looking at ways of fixing that. But for now, yeah. So when you enable preempt RT, here's the big thing. This is the big hammer. This is what's getting into the kernel, and this is exactly what we mean by real time is coming into Linux. It's the option we've been all dreaming of. Turning spin locks into mutexes. They're not really a spin lock anymore, are they? So they don't disable preemption. They don't disable interrupts, even if you tell it to disable interrupts. If you do spin lock IRQ or spin lock IRQ save, nope. It's the same as a spin lock. Same function. Boom. So how do we do this? Why do we do this? Well, the reason why spin locks disable interrupts, if you do spin lock IRQ save or spin lock IRQ, the reason why you do that is if you have an interrupt or a spin lock that's being shared between thread context and interrupt context. So if you were to take a lock and not disable interrupts, and your process gets preempted or interrupted by interrupt, the interrupt handler runs, and it grabs the same lock, boom, deadlock. Don't want that. So this is why we don't need to disable interrupts, because everything's a mutex, everything's schedulable. So you take your lock, your handler, I should have made that smaller. The handler is less than interrupt. I could have made that shorter. OK, I was lazy. Remember, I started this at 5 a.m. So he takes up, the handler, only thing is wakes up the thread. say this time it's not a high priority process going on, so the thread, the interrupt handler goes right away, and it takes the lock. But the thread that had it, the thread that it preempted, or it's preempted now, not interrupted, preempted, and scheduled, had the lock, so it has to block. So it schedules out. It can. Interrupt handlers can now schedule out. You run your task. Once it releases the lock, schedule back in your thread. So priority inheritance. Right now we have priority inheritance within the kernel, but it's only for a few ticks. Fast user space mutex. When you use pthread mutex attribute, so if you use pthread mutex within your application, and you were to say turn on the attribute prio inherit, you actually get priority inheritance, and I'll explain that. PreemptRT does that inside the kernel to all this mutexes, all this sleeping spin locks, and to the mutex. So my talk can't be complete without me doing these slides. I did this. This slide is actually from my first time I ever talked about real time, and it's been every single talk of mine. So it's like me taking that picture where the battery died. The best example of where this could go wrong came in 1997. The Pathfinder flying up to Mars. It started resetting. Suddenly it would reboot, and they didn't know what was going on. It got to Mars, it would reboot. Every so often it would reboot. And like, what's going on? This thing's just normally going on. They'd lose communication for some time, and then suddenly it would reboot. And they would get communication back. And this scared them. So they took all the code, and they were able to simulate the exact same things that was going on up in space down in their labs, and they found out what was happening. They had this process, a very, very low, rare process that seldom ever ran. And let's say it's process C, that's up on the chip. And this process would just collect meteorological, I can't pronounce the word, meteor data. And it would wake up, collect some things and put it onto the bus, and then go to sleep. In the meantime, the bus manager, highest priority process on the system, would be accessing that bus and would have to grab a lock before it would touch that bus. And for some reason, priority inheritance was turned off on that lock, because I think they did it for performance reasons. And they forgot about this little lowly task that was sharing that lock. And what would happen would be the process would wake up, get preempted, the bus manager would go run, try to grab the lock. Okay, I gotta go sleep, go back to sleep. The little logging data continued, and then there was an intermediate process that came in that runs for a very long time. And it started up, and it preempted the guy preempting A. And now when A was stopped, that all bus management stopped. And the system had a watchdog timer go off, and it did a reboot. Boom, it says things are locked up, we gotta reboot the system. So the fix was simply send up a little command. They were able to upload a little switch that turned that into a priority inversion task, or a lock. And they never had a reset, the resets stopped. What happened? So what happens is C goes, once A runs and blocks, it gives a priority, C inherits the priority of A, so it runs A. So when B wants to run, it can't. So it has to wait. So C releases the lock, loses its priority, A runs, it sleeps, B can now run normal. RW locks has been our nemesis for some time. We've done things. I actually wrote code to make multiple priority inheritance. Now priority inheritance, people don't like priority inheritance because it's kind of complex, but I actually even made it more complex. People, I don't know if you know me, but I kind of like code that's complex. I usually like complex problems which require complex solutions. I love that. I evolve around it. So I made multiple things, and Thomas looked at it and says, "No, get rid of it." Okay. So what do we do about reader-writer locks? Because reader-writer locks everyone loves, because you think reader-writer locks are really, really good for multiple CPUs. Because you can have a reader, multiple readers grabbing something, because reader-writer locks are basically, think about it, do a lot more reads than you ever have to write. So if you seldom write, you just do a lot of reads. You want that all in parallel. That's great. So you want that all going out, so reader-writer lock, perfect. So each time a reader goes to look at the data and read, it grabs the lock, fine. Multiple readers, multiple CPUs, all fine and dandy. A writer comes along, it's got a block. And wait for all the readers to finish, depending on whether it's a fair lock or not, that could have issues. But finally, when all the readers are done, it will get the lock and do its data, and then, or do its updates and finish, and then all the readers come back in again. It sucks for multiple CPUs. Don't use reader-writer locks where you don't have to. Use RCU. Get rid of the reader-writer locks. For those of you guys are hardware guys, this is ELC here, I'm sure a lot of ELC people here. Cache line bouncing will kill you. I could show lots of graphs of performance. When you are sharing the same cache line, that is now the bottleneck that we're hitting almost everywhere. Reader-writer locks, that's a bunch of readers hitting the same cache line. We've actually made spin locks special to do the spinning outside off the cache line on local memory, so we wouldn't have the cache line bouncing that was killing everything. So a lot of work's been done to try to make the cache line better, because that's what speeds things up again. If you use reader-writer locks, it's not much faster. You're actually, it's kind of, it does that. The more CPUs you get, it flattens out. So avoid that. With more CPUs with RCU, whoosh, it's still exponential. Not really, but pretend it is. So we compromised. We just said reader-writer locks are mutexes still. So even if you do a reader RW lock, it turns into a mutex, but that's fine. They just won't any priority inheritance. So avoid it for another reason. You can get priority inversion with reader-writer locks now on the RT patch. So avoid those paths. Try to avoid it. We're trying to get rid of it. So that's what we're going. That's what when we analyze real-time systems, we look at the device drivers and make sure we try to avoid all reader-writer paths, or at least make sure that there's no writer involved in any of the real-time threads or anything. But writers do still have inheritance from themselves because they're normal mutex, basically. The tri-lock issue. The tri-lock issue, okay. How many people have ever done something like this? A few hands? You're afraid to raise your hand, you should be. This is, usually what happens is you got this mixture of work where normally, let's say you grab lock B first. Say you grab, your locking orders, grab B, grab A. And for anyone that's not a computer science and you're just here to see me talk, which I think I'm talking very slow right now, if you grab B and A always in that order, you're fine, you're not going to deadlock. But if you ever have any place where you grab A then B, you could deadlock because, you know, the mixture of B, A, oh, we're dead. So we always grab in one order. So one of the ways around doing this, because there's times you're doing some data that requires protection of A, but then you want to do something that requires protection of B, and you don't want to drop your lock and redo everything, so okay, we'll just do a tri-lock. And if we get it, great. Otherwise, we'll drop A and go back and try it again. Because if someone's blocked on A, once we release it, they get the lock, and then they'll release it. So when we get the lock A, we could try it again and do this. This is great, okay? Problem solved. But it doesn't work for, you know, it's great for spinning locks, but not for mutexes. So what you have in a real spinning lock, you have CPU 0, CPU 1. So in the tri-lock, you know, the CPU 1 takes its lock to lock A. CPU 0 takes lock B. Now you want to tri-lock on B, so you actually go into this little loop. You spin while CPU 0 has lock B, and you're waiting for lock B. So what you do is you release A, you grab A again, you try B, fail, repeat. You know, wash, rinse, repeat. Boom, 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 boom. Get nice, pretty colors on graphs. And then finally, CPU 0 releases a lock. Hey, we're done. We got B. We go. We're all happy. What happens when you do it with sleeping spin locks or mutexes on a single thread? And say if the green guy is much higher priority than the yellow guy. So the yellow guy grabs lock B. We go try to take, or we take lock A. Oh, we're going to try to get B. So we go through that whole magic of release A, or grab A, try to grab B again, blah, da, 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 da. And guess what? You preempted A, or B, or the owner of B. You'll never get that lock. So you'll just spin forever. So one solution that's a hack, best is don't do the trick. But if you haven't figured out what to do yet, here's one hack that will work for you. And that is to grab B after you released A. And then release B. And then grab A again. So how does that work? So the task says B, The first task gets B, and then you grab A. So you try to get B, and you don't get it. OK, so what do? You release A, and then take B again. No, so you're going to block. You're almost guaranteed the block now because you tried A or tried B, it's not there. If you preempted the guy, you're guaranteed the block. Boom, B blocks. Not only that, priority inheritance kicks in. Boom, you just boosted that guy to your priority. So even if it's of a lower priority, he gets your inheritance. He'll run. Once he releases B, boom, you get it and go on. It's a hack. It works. Try not to do that. Best thing to do is avoid that little trick. Next thing is per CPU variables. Well, this is when you have a per CPU variable that's only associated to your CPU. This is something that we like to encourage people to do. Use per CPU variables. Yes, this is awesome. Like I said, we don't want cache line bouncing. To scale, you need to do everything as much as you can on one CPU without looking at any other CPUs. That's great. We love it. Well, how do people usually protect per CPU variables? They disable preemption. And sometimes they do it for a long time. And sometimes they say, hey, spin locks disable preemption. So I'm going to grab a spin lock and do my per CPU variable stuff and then release a spin lock. Hey, great, I just protected that preemption there. Well, guess what? We don't disable preemption anymore. But, so this is what you'll see, sometimes you see. Spin lock, let's say I have two per CPU variables. I want to add them together and store them to a third per CPU variable. So I grab A or X, Y, add them to Z, boom, right. Spin locks do disable migration, so this still does work. This is OK. You don't have to change your plans. Preempt RT comes in. It's still OK to do this. We disable migration. So as long as you protect that data by that spin lock, if it's a per CPU spin lock, we do have per CPU spin locks, that's OK. We love them too. But don't do both. So if you had task A that said, hey, I'm doing spin lock here, or one guy does a spin lock, I'm disabling preemption here. No, you're not. And you do your little magic, and task B has another thing where it doesn't need to grab a spin lock. So we don't need to grab a spin lock. We'll just call preempt disable and preempt enable, and you do your same little magic. And what happens here is you get this. So that operation supposedly has to be atomic. So you've got to do all those three commands without anyone jumping in between. Well, guess what? You start yours, you grabbed your spin lock, but you didn't disable preemption. You just stuck on that CPU. So say you have a higher priority process comes in, you get scheduled out, boom, preempt disable, great. Now you turn off preemption, you do your work, preempt enable, fine. So this is bad. But preempt disable itself is not bad. We don't want to tell people it's bad. The only thing is, if you can't see, well, I'm going to tell you this, if you use a preempt disable and you can't see the preempt enable on that same screen that's small on your phone, you did it too much. Something like this, I could put on a slide. Say that to yourself. Could I put this code on a slide and project it where people in the back row can see it? Fine. OK, I think that's good enough. Almost. Don't call functions. There's no functions in between in there either. Don't do this. This is something we've seen. Just because they did something like, oh, I need to malloc something. And they just happen to be in a preempt disable location, and they don't really want to reorganize their code, so they're kind of being lazy and said, I'll just allocate right here, boom. And now you notice it's a GFP atomic, so you have to use the atomic, which is bad in itself, because you don't want kmalloc to schedule out or anything. The problem with this is kmalloc calls spin locks. Spin locks sleep now. So that's not good. We don't do this. Do this. Do your allocation up front. If they fail, don't disable preemption. Do your work. It takes a little more organization. Guess what, though? It's cleaner code. It does. It makes your code much nicer, much easier to look at. People will be pleased. They'll read your code when they go to bed at night. Do this with GFP kernel. So now you do a normal malloc, because you can preempt, you can sleep. Great. You don't have to do these crazy things and get special memory and all that. So preempt disable is not bad if it is short. Keep slow operations out of preempt disable. This is not only good for real time, but it's also good for just the reaction of the system, because it's good for mainline too. Disabling interrupts. So avoid local IRQ save. Most likely, if you're using local IRQ save, it's a bug. There's a lot of times I've seen in old drivers, local IRQ save, where they were written when everyone had a single CPU. They needed a spin lock. I think we got rid of most of those, but that was a lot of things. But you really shouldn't have to disable interrupts. And also, I'd say you're being greedy, you're being selfish whenever you use this, because especially if you're a device driver, and say I use local IRQ save, you're disabling interrupts for everyone else, not just you. Okay? I'd make a political point right now about my country's leader right now, but I don't want to go there. I'm American. Proud of it. This okay. So, anyway, back on track. There is a case where if you have per CPU data that's shared between actual interrupts, and you don't want to grab a spin lock, you could make it. We have something that we have in the real-time patch something called the local lock. I didn't add it here because Thomas doesn't want to add it. He's like, I'm trying to find better ways to write code so we don't need it, but we haven't come up with the situation where, yes, you could have shared per CPU data between the thread and the interrupt handler. So on mainline, the best thing to do is local IRQ save because you stop the interrupt handler going on that way. But then again, you are stopping everyone's interrupt handler. You're being selfish with that too. So best to rewrite your code. Maybe try to find another mutex or spin lock. We have this thing called a local lock, which is basically just a local IRQ save without, or preempt disable, but without on mainline, but on RT, it's a mutex. So it's fine to do. And what's also nice about that is you're annotating why you have this local IRQ save. Because a lot of times, we've actually had this where we go back to you guys developers and say, we've studied this for 3 days. We have no idea why you have a local IRQ save here. And the developer went, oh, I forgot about that. We don't need it anymore. We just deleted it. That was the solution. So the reason why is because they didn't know why they had that local IRQ save, because there's no annotation about it. It's just local IRQ save. I need to stop interrupts or something, but they changed their code, had spin locks. The local IRQ save was not needed anymore. Don't do this. We've seen this. Some people say, hey, I could be fancy. I could put local IRQ save, do a lot of work, and then spin lock, and then spin lock and do local IRQ restore. No, those local IRQs, that's just spreading the pain out to everyone. Don't do that. If you do local IRQ save, you want to keep it with the spin lock. If you're not, move the spin lock out. You're not saving anything. It's not that much, you're not saving any benefit for trying to be clever with where I disable interrupts and where I grab locks. Don't do that. It messes up RT, because local IRQ save is a real disabling of interrupts. And then if you do the spin lock, guess what? You schedule. So, soft IRQs. They are one of the biggest PIDAs to mainline as to us. They have a long history. I'm not going to go and talk about the history. What they do is you raise a soft IRQ. You raise it from the dead. And then you're asking it to run. And it will run when it can. And right now, the way it does it by interrupts. And soft IRQs are in interrupt context most of the time. So if you write an IRQ or a soft IRQ handler or a tasklet or something and think that you're always going to be in interrupt context, you're not. Because there's times when we get too many soft IRQs, we kick off ksoft IRQ data, runs in a thread, and runs your handler as a thread. So we have this thing called local BH disable and spinlock BH. Spinlock BH does actually do something different than it does our other ones, I think. Yeah, because it will kind of do a special lock for soft IRQs. So it disables preemption on preempt RT, but non-preempt RT kernels, but preemption stays enabled. But migration is disabled, so you can use per CPU variables, that's fine. So currently in mainline, soft IRQs are indiscriminate in what they run. So when you raise one, although you might raise the networking soft IRQ, if there's like a block soft IRQ that wants to run, it will run too, and you got to wait for that as well. So there's no way to change the priority between them. There's no way to make it deterministic. So soft IRQs really do suck on mainline. And they hurt. People actually are working on fixing it now in mainline. They're using RT ideas to do so. So we do things differently with soft RRQs, and we went through several iterations to get this right. So almost from probably every 3 years, we wrote the soft RRQ logic completely different. So if you go back well, not now, actually we've been consistent ever since the 4.0 kernel. So 4.0 kernel, I think, is the time we went, hey, we got soft RRQs finally right. But before that, it changed all the time because we had no idea what to do because we wanted to separate them, change the paradigm because we wanted every soft RRQ to have its own priority. So you could run the networking soft RRQ at a priority of like the networking stack, let people change it. So we had soft RRQ threads, but then they caused deadlocks because it changed the paradigm of how things work. And because soft RRQs could run on any CPU at the same time, but not on the same CPU at the same time. So things are really, really weird. And what we finally figured out what we could do is just let whoever said, I want the soft RRQ to run it. Run the soft RRQ. So whoever raises it, that's the priority. You know what the priority is. So if your high priority task raises the soft RRQ, it runs the soft RRQ logic under its own task. Works great. But mainline is currently suffering from soft RRQs with starvation. Like I said, the networking soft RRQs can't run because the block soft RRQs are going too long, and they're having issues with network performance, and everyone wants real good response time, even on mainline Linux. So there's work right now that's going on that's taking ideas from Frederick Weisbecker, who also came through the real-time guys. His work is influenced right now in LKML. The first series I wrote is not the best. And it's going through, you'll see soon, what we're going to do is now start doing annotations. You can actually say, I only want to run, like when you enable or raise a soft RRQ, with the local RRQ save and restore, it's going to record, okay, we know what you saved, and when you enable soft RRQs, it will only run what you enabled. And let everyone else go to ksoft RRQD, that type of thing. So those that are important, like the RCU ksoft RRQD, no one really needs to run that, the RCU one. That's a garbage collector. It can run whenever it gets a chance to run. As long as it eventually runs, that's fine. But things like that don't need to run. And those could take up a long time because those are running like the RCU cleanup code, which could take forever. So you don't want those things running. So we're actually working to get mainline to say, hey, just pick which soft RRQ I'm going to raise, and it's going to be all done magically for you, hopefully. We'll see. We'll find out what the patches from Frederick come in. But the way we do it now is once you do the raise, it sets a flag in the task struct saying, OK, this guy raised it, so he wants this run. We run under his priority. He asked for it. Let him take the penalty for it. So soft RRQs on non-real time looks like this. High priority task raises a soft RRQ, interrupt handler goes off, and then when the handler, before it goes back to user space, it runs soft RRQ handlers, all of them, RCU, whatever it has, it could go off. So this high priority task has to wait for that. So what we do in the real-time task is, say if an interrupt goes off and triggers a soft RRQ within the handler, it will come back, and the handler itself, actually I just forgot, I put soft RRQ. This slide is a mistake. The green should have ran first, then the handler. Swap that. Just in your head, put swap, schedule, there. And then it runs a soft RRQ logic within its handler itself. Finally, what I want to talk about, since it's getting close to being end, raw spinlocks. This is actually our gift from Linus. Back in 2009, raw spinlock has been introduced to the Linux kernel. How many people have seen raw spinlock in the kernel? Just people are just tired, they don't want to raise their hand. Yes. This has no meaning in mainline. Zero, none, niche. We came up with excuses, but they're all BS. This is just a way that we could differentiate when you have a spinlock that can't sleep. For instance, the scheduling spinlocks, the timer spinlocks. Those can't sleep. You can't have the scheduling spinlock schedule. It kind of gets into an infinite loop that way. So there are things you actually have to have as a raw spinlock. Well, this is it. Raw spinlock, scheduling loop, we have it in there. Don't use it if it becomes a problem for you. See, because it makes order important. Yeah, this is what I want to do. You can only use them for critical, usually I would say hardware or scheduling activities, or CPU going down. The major events could use them. not your normal device driver, not saying that, oh, my code is special. Don't do it. If you do it, it could cause problems, and actually it defeats the point of being a preemptible kernel, fully preemptible kernel. The more spin locks, raw spin locks you add, the less real time it becomes. It's less deterministic, it changes time, it's horrible. Don't do it. So your lock is not as important as you think it is. Questions? What an anticlimactic ending. Okay. I think we have like 4 minutes. If there's any questions, there's microphones, because I guess this is being recorded. So come and show your pretty face to the TV. Oh, got someone coming up here. Well,
thank you.
Yeah.
Can you go one slide back, please, regarding if you cannot figure it out?
Yes.
Actually, we had a problem, and it was what you write, scheduling while atomic. I had a lot of error messages in my kernel log, and it was actually because we ported from 4.9 to 4.14 when the IRQ save flag inside the HR timer struct has been removed.
Oh.
And yeah, we got it compile again, but then we saw a lot of scheduling while atomic errors.
Is this for mainline or preempt RT?
A preempt RT patch set.
Have you reported that to Thomas?
No.
Please do, because that could be the case where you said we switched to IRQ. What that means, he removed the IRQ save flag from the interrupt handlers. What that means is he didn't think there was any path that could get there that's not from an actual hard interrupt.
Yeah, we are using it in hard interrupt handlers.
Oh, no, sorry, turn around. Stop it, turn around. I started these slides at 5 a.m., okay. No, I meant the other way around. He thought there was no path that it would be used from a hard interrupt context. He thought to get here, it had to be threaded. And if not, something about his assumption is wrong, or maybe something that your assumption about using that function is wrong. So that's where it's a communication thing. I would highly recommend reporting that, saying, hey, I found the path. When you change this to that, this broke. What can we do to fix it? Or should that be an IRQ save? You can always set a patch and see what happens.
Okay, thank you.
Someone else?
Yeah, right near the beginning you mentioned...
Wait. So were you number 2 there? Or wait, who's?
I thought I was. I was stood up first.
Wait, yeah. Yeah, they stood. Wait. Oh, that's
I
you.
moved.
Oh, geez. I'm like,
I thought I'd queue patiently so I could take part.
Oh,
effectively
yeah,
quickly.
you're right. You know, it's just that the speaker's over here. I thought someone was yelling. Okay, go.
I beg your pardon, sorry. You talked about basic RT at the beginning and then the do me full RT.
Yes.
What was the difference between those two?
I believe it's been a long time since we used it, and we kept it in, and it's one of those things that if anything breaks, we come back. Actually, what I believe, it turns on everything but the spin locks, sleeping spin locks. It does everything else. It does this threaded IRQs, everything else. It's just to say, basically it's a way is it the bug because of the sleeping spin locks, or is it a bug for something else? Because basically the sleeping spin locks is the big thing that we want. Everything else is kind of like, there might be a bug there too. So when you have both on, it's hard to differentiate. I've never used it. Thomas, I can see, still uses it. Because I said, should we get rid of that? Because he doesn't expect that to go into mainline. That's the one thing he wants to rip out before it actually makes it into mainline. I only put it up there because if you download and install the preempt RT patch, you'll see it. I just want to explain what it was. Anything else?
Yes. Slide comments. You put on some slide, use RCU if you can. I could correct it if you may, because RCU only for high priority tasks. Better to use mutexes.
Yes, I would say you can and may are two different things. Reason why I say use RCU when you can, which means that it's not going to suffer the performance and everything else. Because yes, RCU is extremely fast for writers, extremely slow for readers. Sorry, swap it. I need more coffee. Extremely fast for readers, horrible for writers. So yes, if there's a case, you could do it, but yeah, it's going to kill your performance because you have a lot of writers. That's the case. Maybe you could try to rewrite your code. As I've actually worked to try to rewrite and get rid of the writers or put them elsewhere and try to constantly piggyback and use more RCU because that really, RCU scales, RW mutex does not.
Okay, thank you. Yep. And one more comment about drivers and actually this slide. Row spin locks, we did several patches to fix GPU drivers because they implement in RQ chips. So in some drivers, it's only way.
Okay, I'm going to say something. The reason why I said it so strongly is I don't want people, because I've seen it thrown too quickly. There's been a few cases where we said, okay, they grabbed a lock that's only, basically it's the same thing as the preempt disable thing. If you could see on your cell phone or on a slide with no function calls, just grabbing the lock or this raw spin lock and only a few things, and it's, I think Slab we might do this too, because it never grabs it and does anything for more than a very, very short time. That's perfectly acceptable. But anything more than a screen full or function calls within it, no. Does that make more sense?
Yeah, but with GPU drivers, it's basically I/O with registers, so nothing else.
We have to, well, we're slowly fixing one thing at a time.
What is in place? What is in place and being put into place to help catch regressions early on preempt RT?
Are you coming to Plumbers? Crap. Anyone coming to Plumbers? Linux Plumbers. We actually have an RT micro conference. That's actually one of the agenda. How do we catch the regressions? Because like I said, at the beginning of the talk, I said we got it in. Great. Oh no, we have a lot more work to do. That's one of the topics. We have ideas, we have answers. I'm not saying anything yet because it's still a work in progress.
What about seglocks? Is good for IT? Bad for IT?
Try to avoid them if you can. They're not good for mainline. No, they're not. Because they're like a repeating lock, you know, like, oh, we did it. I mean, it matters how much contention there is, but that's one of those things that's okay. I think RT, if I haven't looked at the code recently, I think we do make it more deterministic, because right now that's a non-deterministic functionality, depending on your load or stuff. But most of the time, like in catching a timestamp, because that's usually a reader, that's usually not something of a prior. Most paths that hit that are not usually real-time tasks. So if it's not a real-time task, we really don't care about determinism, but that's one of those things you have to audit. So yes, SIG locks are, yeah. Anyone else?
Yep. Over here. Are we still trying to get rid of the semaphores? The traditional ones?
I don't think we've seen much left. What's left?
No, they're actually getting more.
Oh, what?
The semaphores, yeah, they're getting added faster than they get removed. We were down to 30, I think, at some point. Now we're over 100.
Good to know. Thank you. You know, yeah, we would love to get rid of that.
I have some ideas about how we can improve that. But
are you going to be at Plumbers?
yes.
I'll see you then. Anyone else? Well, you got to come up and get a mic. It's being recorded. Unless it's a short question, I can repeat the question.
So if it's in, what will happen to the patch set?
Okay, the question is, if we get preempt RT into the kernel, what will happen to the patch set? Will it go to 0? Hopefully, yes. We might have a niche patch set for things that, there are some things in the kernel that may not get into the mainline that's for some device or for some weird situation. We may have a patch set just to do that. It may just be like a staging to try to get the mainline, come up with a new solution, that. But the big hammer is that sleeping spin lock. Once that's in, that's real time. Everything else is sort of one of these little fixes. Everyone looks at the patch, say, wow, you got 300 bytes or 300 patches in there. 290 of them are basically little fixes like that. So it's like once we get one thing into mainline, it'll take out 200 patches. So because those 200 things are hacks because we don't have a solution for this one thing. Once we get that solved, boom, those go away. We may have little things like that, but hopefully everything will. Yeah, it'll be optional. Yes. At that point, it'll be something that you could. It's going to be for those cases where you just have like someone. I want to get this in, and we say that's not a great solution, but we may maintain like a patch set for those cases where we don't really have a real solution for yet. But those are like that's going to be for the 99.9% of the people here. You won't care about that. In fact, I probably would never run it. It might be just like, hey, I got this. Okay, we got to figure out how to solve that. Here, we'll put this patch here so everyone that has that same issue could use it, shared. The Linux kernel really is always forked. Everyone says, you know, people always say, what happens if Linux gets forked? I hate to say this, there's hundreds of thousands of Linux kernels out there, not one of them are like those hundreds of thousands are the same. They're all forks. Android, even Debian, Red Hat, they're all forks. Red Hat has its own system. They have their own patches. SUSE has their own patches, same thing. Anything else? When will it happen? We were hoping this year. It looks like because of recent events, it's not going to happen. It has nothing to do with technology. Anything else? Okay, thank you. Oh, wait. It's actually, well, yeah, go ahead.
Sorry, practical, just very practical. Is this, I mean, with all these things, are we getting really deterministic clock cycle? You know, it'll happen within this many clock cycles? Or are we just saying it's guaranteed 99% of the time, that kind of thing? And what is the time, the latency that we're guaranteed to, the jitter?
That is not determined by the RT kernel. It's determined by your hardware.
Thank you.
Yes. Thank you.